This is going to be, again, different from other stuff a bit. Not as different as the nuclear chapter, but still pretty different. If you go on and take more chemistry, you'll notice if you take organic chemistry, it is a totally different kind of a class than the regular kind of general chemistry. We got no calculations in this chapter. We got no math problems. We got pictures, we got diagrams, we got rotating structures in your head and trying to picture things in 3 dimensions. So it's just kind of a different way of thinking about how chemicals work together. I like it. It was one of the things that made me excited about chemistry in the first place. So let's talk a little bit about what it is, and then we'll introduce some of the compounds that we're dealing with. We're not going to go through this all the way until 4:45. We'll just do like we would do a normal class period, and then we'll be done. So, anybody know, have you heard this term organic chemistry before? Yeah. What is it? What do you know about it? It's complicated? Like the topic, or it's complicated what you know about it?
Drawing stuff.
Drawing stuff? Yeah, carbon chains, yeah, sure. What else? Yeah, that's all right. You know anything else about it? All right, well, how we define it now is what we're going to be dealing with is the chemistry of compounds made primarily from carbon, and then also nitrogen, oxygen, hydrogen, and some other stuff. But mostly, the thing that we're going to focus on mostly is the chemistry of carbon, and you may have heard that as organic chemistry is the chemistry of carbon. Where the word comes from initially is it was thought that there were 2 distinct branches of chemistry. That there were compounds that came from nature, from like rocks and the ground, and mineral compounds. That was called inorganic chemistry. And then there was organic chemistry, which came from living things. And for a long time, it was thought that those were totally different classes of compounds, that you could never synthesize something that came from a living thing because it didn't have a life force or something like that. And now we know that's not true. We can make all these molecules however we want, and there's plenty of inorganic stuff in living things too. But we keep the distinction because organic chemistry, for the most part, focuses on building molecules that are meant to interact with biological systems. So since we are mostly made from carbon, nitrogen, oxygen, hydrogen, and some other stuff, if we want to make molecules that interact with us, then we need to make those molecules out of the same things. So that's kind of how that came about and why we still call this separately organic chemistry. All right, so to talk about this, if we're going to talk about the chemistry of carbon, we have to look at the structure of carbon and the types of things that it makes, and then we can start looking at what those compounds are like. So let's review from a while ago. How many valence electrons does carbon have? How many valence electrons? 6 total electrons. How many valence electrons? 4. 4? It's in column 4? All right, everybody do some reviewing for the final when you get a chance. Just saying. And so we got 4 valence electrons on carbon. And that means that there are these kind of 4 spaces, right? Because we want, everything always wants 8 electrons. We talked about the octet rule, wanting to get up to 8 electrons. So we talked in a previous chapter about how carbon kind of has these 4 spaces where it can share electrons and make covalent bonds. And that leads to carbon usually getting 4 bonds. So we can look at a compound like this. And say that this is generally the way that carbon is going to behave. And one of the features of organic chemistry, and one of the things that makes it really usable, is it's really predictable. Some of the simplest rules that we've learned this semester apply all the time to organic compounds, whereas some of the other stuff on the periodic table plays with those rules a little bit. So we can be pretty confident in how carbon is going to act based on the types of situations that it's in, and that makes for a really predictable chemistry. So if we take a molecule with 2 carbons, again, we have to have enough other things there to make sure that carbon always has 4 bonds. Carbon can double and triple bond as well. And then we would have fewer hydrogens bound to it because the double bonds count as 2 bonds. So in a molecule like that, again, each carbon has 4 bonds. All right, and these are examples of what we would call organic molecules, molecules based on carbon. Now, one thing that we are not doing exactly correctly here is we're drawing these structures out in this grid, this 90-degree grid. And the structure of carbon with stuff bound to it is not actually like that. It's a little bit more 3-dimensional. So I'm going to pull this up in a computer program here so we can watch it. I'm going to draw carbon over here. So I'm going to make a carbon atom. And then I'm going to connect those 4 hydrogens to it. It's going to look weird for a second, but I'm going to make them into hydrogens. Hydrogen, 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 hydrogen. All right, so there's our methane molecule. That's carbon with 4 hydrogens on it, CH4. But if you look at what that actually looks like over here in 3 dimensions, it's like this. So you can see it's not a flat shape with everything at 90 degrees. It's actually this very 3-dimensional, almost pyramidal type shape. How might you describe this shape? What? No, how would you describe it? Anything. Like a jack? Does everyone know what a jack is? Yeah, so it kind of looks like that, right? It has these 4 hydrogens with the carbon in the middle. If we look at those angles, so if you look at the angle here, would you say that that's wider or narrower than 90 degrees? It's wider, right? You see that? So that's why that's one way that we can explain what's going on here, is that if it were actually 90 degrees like this, those big hydrogen electron clouds would be much closer to each other. We know electrons want to repel each other as much as possible. So if they can spread out in 3 dimensions, since there's no reason for them to be flat, they will spread out and make this type of a shape. So let me get this in the right position here, and then I'm going to copy it over to the notes. So we can draw on it. All right, so there's our shape of that molecule. We've got carbon here, hydrogen, 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 hydrogen. And these angles come out to about 110 degrees. So wider than 90-degree angles. And the type of shape that this is, we say is tetrahedral. Call this a tetrahedral shape. The reason we call it that is because if we imagine connecting those hydrogens together, let's see if I can get a better color here. Wait. So if I kind of make lines like this, connect those things together, that makes a shape called a tetrahedron. It's a regular shape, a regular polygon with 4 equal sides, 4 equal edges, 4 equal corners. And that's where that word comes from. So if you imagine the carbon in the middle of that tetrahedron, and then the hydrogens all on the edges of the tetrahedron, that's the shape that we've got. So we call that a tetrahedral geometry. And that geometry controls a lot of the structure of these carbon-based molecules, because carbon always has to be in that kind of a geometry. We'll see it changes a little bit when we get into double bonds and triple bonds, but basically stays in that geometry. So how do we draw something like this in the 2 dimensions that we've got for our paper? If you're good at drawing stuff, you could probably, you know, do it with shading and whatever and make it look all pretty. But if you just want to communicate that it's a 3-dimensional structure without having to actually draw it beautifully, how could you do that? Well, we have some conventions in chemistry. And the way that we usually express this is we take 2 of the bonds and we draw them as straight lines, saying that they're in the plane of whatever we're drawing on, so they're like flat. And then we would say, okay, one of the other ones is coming out toward us, and the other one is going back away from us. Does everybody see how those other 2 hydrogens are kind of coming out and going back? The one coming out, we draw with this wedge-shaped bond, like that. And the one going back, we draw with a dashed line like that. So that shows that geometry, and that way we can draw it in 2 dimensions and make it look a little bit more 3-dimensional. So if we were to draw this on regular paper, it might look like this. And that way you don't have to have perfect angles or everything lined up perfectly, but we understand what we're drawing there. That we've got 2 bonds in the plane of the paper, and then one going back and one going forward. So if we expand that then, one more carbon, we might draw it like this. And by the way, it's still okay to use this notation, this 90-degree notation, when we're trying to communicate how things are connected. But if we're trying to communicate 3 dimensions, that's not really going to cut it. So that's how we might draw 2 carbons together with hydrogens around them. If we wanted to show it in 3 dimensions, we might draw it something like this. With these dashes and wedges. This pen is being a little squirrely, sorry. Those are the same molecule. The bottom one gives us a little bit more of a picture of what it might look like in 3 dimensions. Another important facet of these compounds is that single bonds rotate. Single bonds can rotate. So we can also draw this thinking about rotating around that central bond. And have something like this. Which is another way to think about that molecule. We can show that in this thing here. We can go back over here and draw another. So you can see how that looks there. So you've got the hydrogen, carbon, carbon, hydrogen, coming out, going back, coming out, going back. And then we can I don't remember how to do this. Oop, not like that. Well, it's doing something. So this is actually an energy calculation. What it's doing is calculating all the different possibilities for how those things could be arranged and finding the best energy, the best version of it, the highest energy version of it. And we could let that go for a while, and it would figure out essentially that we had it right the first time. So that's the best way for these things to be arranged based on whatever parameters were built in there. I was trying to get the things to rotate, but I'm not sure how to do that. So, okay. So those are some different ways of drawing the compounds. So now, just so we know what we're talking about, we're going to look at some different ways of drawing structures with some different size molecules. Start small, get bigger and bigger, and we'll also start learning some of the names of these things. We make a couple categories here. We can say molecular formula. Name. And then the book calls this the expanded structure, which is what we've been drawing. And then we'll notice that as we get bigger, these expanded structures become pretty tedious to draw. So we're going to also learn how to draw a condensed structure. All right. Let's start small with CH4, which we call methane. It's an important part of natural gas produced by living things. Its expanded structure, we've already drawn, is just the carbon with 4 hydrogens attached to it. And it's such a simple structure that its condensed structure actually looks just like its molecular formula. So that's also CH4. So we'll see what a real condensed structure is in the next one. Next, we've got C2H6, ethane. So this is the 2-carbon compound. The expanded structure we also drew is 2 carbons with a bunch of hydrogens around it. And now we have a chance to draw a condensed structure. So in a condensed structure, we take that large expanded structure and we condense the hydrogens down onto the carbons that they're connected to. So instead of a C and a C and all the H's shown, we draw the C's, but then we draw the H's right next to them with a subscript saying how many there are. So for this structure, we would say CH3 and then CH3. Rather than drawing all those hydrogens out, we just say there's 3 hydrogens on this carbon, there's 3 hydrogens on this carbon. And that saves us a little work. You'll also sometimes see them, if they're a simpler structure like this, you'll see it drawn without that line in the middle. So another way to draw the condensed structure is to just put them right next to each other like that. That's kind of like a molecular formula, but these types of formulas are more useful in organic molecules because they're all made from carbon and hydrogen, all the same stuff, and a lot of times they have the same or very similar formulas. So the molecular formula isn't usually as useful as like a condensed type formula that tells you something about how everything is connected. Let's look at the next member in the series here. It's C3H8, and that's called propane. That's the gas that you get in the big tanks to burn in the grill and all that, or you might run your house on it. And we can see here that it's starting to get a little more tedious to draw these expanded formulas with all the hydrogens. And so again, we can condense that structure by saying how many hydrogens are on each carbon. So we can go CH3, CH2, CH3. Or we can just smash them all together and say CH3, CH2, CH3. For the next one in the series, I'm just going to give you the name. It's called butane. It's got 4 carbons. See if you can draw all the rest. Fill the rest of the table. So start with 4 carbons in a line. Add the hydrogens, count them up, and then see if you can draw a condensed formula and the molecular formula. Did you find it? What did you get for a formula? Yeah, C4, H10. And then hopefully you got something like this. And then we can draw the condensed formula. Whoops, not 4. 3, CH2, CH2, CH3, or you could draw out the lines in between. Okay, good so far? So that's molecular formulas and condensed formulas. That's the new parts here. We'll come back to these names on Thursday when we talk more about naming. Let's move on now to a new type of structure called a skeletal structure or a line structure. So I'm going to make a new table. And now as we get into these bigger ones, we don't care so much about the molecular formula. Don't really want to write the expanded formula because it gets too tedious. So let's just look at the name, the condensed formula, and then we'll add this new one called a skeletal or line formula. And we'll start with the one we just did, just to keep it consistent. So we'll do butane again. We'll do a condensed formula, either with or without lines. And I'm going to show you this new thing called a skeletal formula, and you'll see if you can figure out what I'm talking about. Hold on, came out weird. Let's try again. So that's it. That's the skeletal formula. And that tells you just as much information as all the rest of the stuff. But it's a lot easier to draw, a lot faster. So let's talk about how it works and why it works. So can anybody see where do the carbons go? Yeah, they're the points, right? So we had, in this structure, we could number these carbons, 1, 2, 3, 4 carbons. And over in this structure, that corresponds to these points, either the ends or the vertices, the inflection points there. What about the hydrogens? How are we going to know how many hydrogens are on each carbon if we don't draw them in the skeletal formula? Any ideas how we can figure that out? So if I said, like, how many hydrogens are on this carbon, number 1? In the condensed formula, you can see there's 3 hydrogens on carbon number 1. But here in the skeletal formula, you can't see that. So is there a way to figure that out? Because otherwise, it's not a very good abbreviation. No ideas? We use the predictability of carbons bonding. So way back here, we said carbon generally almost always gets 4 bonds. So that means if we draw a structure where we show a carbon with 1 bond, then we can assume there must be 3 more hydrogens to make it to 4. In here, we can say, okay, we've shown 2 bonds, so then there must be 2 more hydrogens here because we got to get to 4. So as long as we keep that in mind, that the carbon has to have 4 bonds, we can always assume that the extra spaces are taken up by hydrogen. And so this formula can give us just as much information in that way. All right, let's try the next ones. They follow kind of in the same way. We're going to do it like we did before. I'm going to give you the names, and I want you to try to give me a condensed formula and a skeletal formula based on the example that we have right here. So after butane, we have pentane with 5 carbons, hexane with 6 carbons, heptane with 7, octane with 8, nonane with 9, and decane with 10. So see if you can draw condensed formulas and skeletal formulas for each of those. No, start. So you can see how even the condensed formula starts to get tedious as you get more and more carbons, right? But the skeletal structures stay pretty easy and fast to write. So we got 5 carbons for pentane, makes it kind of look like an M or a W, depending on how you started it. And then hexane. Whoops, that's not right. Need one more. There you go. And that, what I just did there, is the biggest mistake I see people make, or the most common one with these line structures or skeletal structures, is just not making enough little bends or whatever. So it's always worth going back when you draw one and counting it out. Make sure you have the correct number of carbons. You don't have to like write it, but just to count it out and go, okay, I've got 1, 2, 3, 4, 5, 6. I got them all.
Can you just write it down?
Doesn't matter. You can draw them sideways, you can draw them however you want, as long as there's enough zigzags for the right number of carbons. So there's heptane, octane, nonane, nope, too many. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. All right, I'm not going to write in all the condensed formulas. They're in a table in your book if you want to look them up. But those are what we call the alkanes. So that whole group of compounds is named the alkanes, which are the molecules that just have carbon and hydrogen with just single bonds. And this isn't all of them, but this is kind of the basic straight chain ones. So what we're going to look at next is what happens when there are more possible ways to write these things with the same atoms. So let's take butane, for example. Butane is C4H10. But there are 2 different ways that we can make molecules that have formula C4H10. One of them is the one we just drew. So we can put 4 carbons in a row like that with their hydrogens. Okay, that's one way of doing it. But there's another molecule that has the same formula, but is connected a different way. And that is if we draw 3 carbons, and then instead of connecting the 4th one onto the end, we connect it to the middle one right here. Now, how can we tell that that's a different molecule? First of all, we counted up, it's got the same formula, C4H10, 4 carbons, 10 hydrogens. How can we tell it's different? Well, it's connected differently. One way to check that is to look at the carbon chain right here. So this is 4 carbons connected in a row. Another way we could describe that is carbon 1 is connected to carbon 2, carbon 3 to carbon, or carbon 2 to carbon 3, carbon 3 to carbon 4. If we look at the other one, we can't make that same kind of statement. We would say, in this one, carbon 1 is connected to carbon 2, and then connected to carbon 3, but then carbon 4 is connected to carbon 2. And that's not the case in the first one we drew. So that is a different molecule. It's a different chemical. It has different properties. It'll have different boiling points, different melting points, all that stuff. It's a different compound. And the relationship between these two is called isomers. Isomers are molecules that have the same molecular formula, but the atoms are connected differently. So those two molecules have the same formula. They're both C4H10, but they're connected in different ways, and that makes them different molecules. Let's try to draw those skeletal formulas of these two. The one on the left we've already done. The one on the right, so how do we draw these skeletal formulas? The best way, I think, the way I would recommend is find the longest continuous chain of carbons. So how long can you make a chain without like picking up your pencil and drawing something else? And this one on the right, it's 3. You see that? You can go 1, 2, 3, but then you got to stop and pick your pencil up to draw the other one. So that means you start with a 3-carbon zigzag. 1, 2, 3. And then you have to add anything else that's connected. So in this case, carbon number 4 is connected to carbon number 2. So I got to make sure to add that 4th carbon coming off of number 2. So that's what the skeletal formula would look like for that second structure. If we want to number that again, it would be 1, 2, 3, and then 4 would be down here connected to number 2. When you draw a skeletal structure, always check to make sure that everything's connected the right way. All right. So that's isomers. So now I've got an activity for you. I want you to find all the isomers that have the formula C5H12. So these are the pentane isomers. How many different ways can you draw structures that are different that all have the formula C5H12? I would recommend you go about this by just focusing on the carbon chains the way we did up there. So see how you can rearrange 5 carbons in different ways, and then add the hydrogens and make sure you can fit all the hydrogens on there. And then, of course, you have to still follow the rules. Carbon has to have 4 bonds all the time. So see what you can come up with. When you think you've got one, come draw it up on the board here. You don't have to be confident about it being right, but we just want to get a collection of structures so we can start to talk about what they look like and what some different ones look like and why some work and some don't. You can draw them in any type you want. You can draw them in skeletal formulas and condensed formulas and expanded formulas, whatever you're more comfortable in. Yeah. Yeah, come on up and draw one. There's plenty of markers, so anybody who finds one, come on up. Okay, thanks. Thanks.
The skeleton.
Yeah.
1, 2, 3. Yeah.
Who's the other one? There's a couple more up there. Anything that you have that's different, that still has 5 carbons and 12 hydrogens. Thank you. Any more? Get some more up there. Got lots of people in here. Somebody's gonna have something different. All right, so I'll give you a hint. Of those 4 structures drawn there, 3 of them are actually the same molecule. And there's still one more isomer that's not drawn yet. Anybody find it? There's one more structure that is not up on the board yet that is an isomer. There's 3 total isomers of pentane. See if we can find it. Thanks. Right, thanks. There's still one more though. That's all right. Let's stick with what we got because we got a good mix of it. Thank you everybody for putting those up there. All of these structures are good, correct isomers of pentane. They are all versions of pentane. The only issue is that 4 of them are the same. Now, how would we know that? How can we interpret or critique these structures so that we know that they're the same? And the way that we do that is that we have to recognize what we said up there before, that single bonds can rotate. So any structure that involves like rotation or bending of the bonds is the same thing as when it's all straightened out. It's only when things are disconnected and connected in different places that we actually get new and different structures. The best way to analyze that, I think, you can see it however you want, but I think, is to use that numbering system and think about what's connected to what. So let's go way back to this first one over here on the left. See that? You see that okay? So I'm just gonna, it's arbitrary. I can number it however I want. I'm just gonna go 1, 2, 3, 4, and then 5. So one way I could describe that is I've got a chain of 4 carbons with a 5th one coming off of carbon number 4. Or I can think of that as carbon 1 is connected to 2, 2 is connected to 1 and 3, 3 is connected to 2 and 4, 4 is connected to 3 and 5. So some way that you describe that in your head of how everything's connected together. Now let's compare that to this next one here. Let me get over close so you can see that. So we can describe this one here in the same way. We can say that it is a chain of 5 carbons connected together. 1 to 2, 2 to 3, 3 to 4, and 4 to 5. The other way to do it, or another way to do it, is circling the carbons like I did up there. If we think of this as a continuous line of 5 carbons, then so is this. Right? It bends, but single bonds can bend, so that's okay. So then which of these other ones are also the same as those two? The other two on the end, right. So once again, we have 5 carbons in a row. And 5 carbons in a row. So that means that this one is actually different, because we can't describe this as 5 carbons connected in a row. If we start circling here, we can get 3, 3, we can get 3 this way, we can get 3 this way. There's various ways we can get 3 in a row, but we can't get 5 in a row. Any way we describe this one has to be a row of 3 carbons with like 2 more coming off of the middle one. Okay. So now look back at what you drew. There's one more isomer that's not represented up here. Does anybody have something that's different that isn't one of these same structures? You got it?
Moving the last one over.
Yeah, that would do it. So if we, let's try it over here. So we put 4 carbons down there. If we connect that 5th one to either end, we still have 5 in a line. But if we connect it somewhere in the middle, like here, now we have a different structure. Because now the most carbons that we can follow without picking up our pencil is 4. We can go either way, but it's only 4 carbons before we have to pick up our pencil. All right, so if we draw the rest of that here. All right, so we've got, we'll just say the most direct ones here. We'll call this one 1, 2, and 3 isomers of pentane. So now the trick is, let's see if you can draw them in those skeletal structures. So can you draw those 3 molecules in the skeletal form? One of them is the same as what we did at the table. The other 2 are going to be a little bit different, so see what you can come up with. Anybody feel brave enough to come draw some structures? Who else wants to come?
Wait, someone did this one? It's all yours.
What?
What?
talk about how there's a slightly better way of doing it.
Shit, I don't know.
One versus another.
Can I just do this one?
Yeah.
Like that one, shoot. Now about from.
Yeah, so you almost got this one, right?
Couldn't you just brought a line, like where I got?
Yeah, you got it. Right, so in this one, what you would do here is, you got your 3, you got the 4th one coming off the top, so the other one, you just, oh, I got the wrong color, but you just draw another one. So you got 2 things. Now, that said, there's a slightly better way to do this. So let me show you how I would draw these in the line structure. So the one you've got correct would just be like that, right? And then this other one, when you draw the line structures, you want to maintain the widest possible angles of the skeletal structures. So yes, it's technically correct, and I wouldn't mark it wrong if you draw one up and one down. But kind of drawing 2 of them like this and making more of a T shape is probably a better way to go about that, because that keeps the angles more like those tetrahedral angles. Similarly, if we look at this one, number 3, let's say I start with my 4 like this, and then I want to make one coming off of that 3rd one. So I have a couple choices. I can go like this, or I can go like this. Which one do you think looks better? The second one, yeah. When you keep those wider angles, keep those same kinds of angles going. It's not technically wrong to draw it down. It's okay, but better to just draw it up so it looks a little bit nicer. You don't have to preserve the direction here. So if we're drawing 4 in a row, I picked my zigzag starting up and going down, and that means that the 3rd one from the left is kind of pointing up. So I should make my bond going up. If I had started that down, up, it would have been the opposite. It doesn't matter that this one is going down. All that matters is that everything's connected to the right things that they're then connected to. So only the connections matter, not the directions in these types of structures. So there's our 3 isomers of pentane, and they have totally different properties. Higher, lower boiling points, different types of flammability, all that kind of stuff, just because of that structural change. All right, so for the last thing we're going to do today, we're going to look at one more set of these. These things get a lot harder just adding one more carbon. So we add one more carbon, we get hexane. There are now 5 different isomers. So this time, rather than trying to figure this out one by one, I want you to work with the other people in your table or around you, or however you want to group yourselves, and see if you can come up with all 5 as a group. And look at each other's structures and try to see, like, oh, okay, that one's actually the same as this one. Make those kinds of distinctions. And we'll see if any group can find all 5.
Yeah, so we did this one.
All right, everybody got them? No? Got a couple? How many you got so far? 4? How many? How many y'all got? 4? 4? We got the 5th one? You got 5? All right, does one group or a couple groups want to come put your selections up on the board here? You can all come as a group. You don't have to just send one person, but I'll come up and there's plenty of markers. You can put them all up here. Maybe one group can kind of go over here, and another group can go over here, over here.
Oh, that's not. Oh, I was just thinking. Just one or?
Put all the structures that your group found.
Oh.
In whatever form. If you want to just draw the carbons, so you don't have to draw the hydrogens for now, that's okay. So we can just see the different connectivities. And then as a class, we want to look at some of these different ones that people found and see if they are actually different or if they're the same.
You have to draw the skeletal thing?
No, draw however you want. You can just draw like that, so that you have to do all the H's everywhere. Or however you want to. You can hear the rest of your group members to help you out. Yeah, I just want to see if everybody had different ones. Okay. So what do you think about these? Is that for the four from your group?
I didn't.
Oh, okay. So what did your group members think about it? Did you talk to them? No. Okay. So we'll talk about it as a group. So what do we think about those? You want to jump off and put some? Yeah, go for it. Thank you. All right, thanks. Have we found any other ones? So we've got a bunch of them up there now. Are any of them the same, or are they all different? What?
1, 2, and 3.
How do you know? Yeah, so that's always a good idea with these. If you can kind of straighten them out. And by straightening them out, I mean, can you make the longest possible chain of carbons and then make that straight and then make everything else come off of there? So like this one here, there's nothing wrong with the structure. There's nothing wrong with any of these structures. But if we're looking to see whether things are the same or not, it helps to put them all in the same format. So what we might do is think about like, let me get another color so you can see this. On this one, we might say, well, really, like, these 5 are all in a line together. You see that? And then this one's coming off the middle. So it might be a little easier to see if we draw this more like 5 of them in a line with one coming off the third one. That's the same structure, but we kind of stretch it out so that we can see it a little bit better this way. All right? Same with these. So this one's nicely stretched out 6 in a row. But actually, all the other 3 of these are also 6 carbons in a row that just need to be stretched out. So these 4 are all the same. Those aren't separate isomers. Those are all the same structure. They're not the same as this one. They're a different one. But they're all the same isomer that we might think of as just this one right here. All right, so over here, what do you think? Is this one, if we kind of think about that, is this the same as either of those two? It's not. You've got a line of 4 and then 2 of them coming off right here. What about this one? Is this the same as one of them?
No.
No, but again, this one could maybe benefit from straightening out, right? Because we can, our longest line of consecutive carbons is 4. So we could maybe draw this as 4 of them with one like this and one like this, if we imagine kind of straightening that out like that. Is that the same as this? Yeah. Yeah? No? Yeah? Yeah? Let's think about it. They're both lines of 4 carbons. This one has 2 carbons coming off of, let's say, the second one in. And this one has a carbon coming off the second one in from this side, and the third one in from this side, or the second from this side and the third from this side. So these are different. Those are connected. They look kind of similar, but they're connected in different ways. So here are our 4 isomers so far. We got 1, 2, 3, and 4. There's one more. Anybody find one more?
Or 2 and 2, like 2 on top of each other on top.
So
That makes sense. 4 in a row, and then just pick one at the end, and then put C and C on top of it.
like that?
Right?
Oh, we got the 6 in a row again, right? Good try. Like this? No?
Stack them on the second.
Stack them on the second, okay? That one different? So now we've got a line of 5 with a carbon coming off of the third one in. Is that the same as any of these other ones? Yeah, it's frustrating, right? Yeah, that's the same as this one. So every time you draw it, you got to look back at the other ones. But actually, this is the most important part of this exercise. It's not finding all the different isomers isn't the important part. The important part is being able to look at different structures and recognizing whether they're the same or whether they're different. Because that's something that comes up all the time in this because of the weird way that we draw all these things. We're going to find some different techniques to help us do that. But anyway, the final one that is not expressed here is a line of 5, but with another carbon coming off the second one in instead of the third one in. So that's the missing one right there. This is a different structure. So this is our fifth isomer.
Can we do first, second, and more different?
From where? How many carbons first? 4?
4 carbon in line.
Yep. And then where? Second?
It's the same.
It's the same, right? Yeah. So different ones end up being the same.
I might be for 7 carbons.
Yeah, we're not going to do 7 carbons because you have one in there. All right, so these are isomers. This is how you build these different ones. The next thing that we're going to do, well, let's just do this right now, and we'll do that. It'll be our last thing for today. Let's draw those skeletal or line structures for these 5 isomers that we found. See if you can draw 5 skeletal structures for the 5 isomers. So as you're drawing these, think of drawing them the same way we thought about them here. Think about the longest possible chain of carbons, make that your zigzag, and then bring the other pieces coming off of whatever spots they need to come off of. So like this one, you make a zigzag of 4, and then have 2 more carbons coming off that third one from the left. I'm going to draw these in about the same order. I'll turn the screen off in case you're still working, and then we'll put it back on once everybody's thought about it. All right, everybody give it a try? You want to see them? All right. Here's what I got. So you probably got some of them. If some of yours look a little different, think about it. As long as they're connected in the same way, they're probably okay. If you have a question, let me know. Yeah. Yeah, that's fine. It's just we usually draw the whole arrow. All right, so that's all we're going to do today. I'll see you Thursday. We'll talk more about structures, and we'll start getting into reactions of these things. Or 11? Yeah, 11. Oh yeah, turn in your lab reports from last week, please, if you haven't.